So good afternoon. Welcome to lecture 3, which is going to be on frequency response. Somewhat of a review for you still, I think, for some of you. Some of you, there may be some new stuff in this lecture. I guess, should I still ask for a show of hands whether you can hear me or not? I think you can, so I won't really ask for that. So just some announcements, and I see some messages on the chat right now that I'll address. But first, homework number 1, you know, is online. It was online last week. It's going to be due this coming Friday. Discussions happen this week. I guess one already happened today. Your labs start next week, but Monday, September 7th is a holiday, so the Monday lab will actually start 1 week after next. The Tuesday lab starts on September 8th. And in terms of labs, they're not up online yet on the website. I guess someone's talking about that one thing that is showing there that really ought not to, the lab instruction manual. That will soon be up, and so will Lab 1. At least the Lab 1 pre-lab will be online soon. So this semester what's going to be happening is you're going to get the labs. Okay, hold on, let me make sure my audio. So you're going to get the labs online, but you might not get the whole lab immediately. So we may put the pre-lab for Lab 1 up, and we may get the whole lab up there. The reason why is because we may be making some last-minute corrections to the old lab, where we're correcting things for the new equipment that you have, which is different, of course, from the equipment that we've been using before. And so I guess let me stop here and ask if there's any questions logistically about the class. So you all should have gotten the form, the Google form from David Au, and filled it out to give your address information, and we're going to use that information to actually send you the lab kits. Any questions about anything right now about the class? Okay, and I see that things on the chat are being answered by Kieran and Tu-Cuong. All right, so today what we'll be doing is finishing that digital communications example. We'll then be reviewing impedance and frequency response, and if we can get to it, we'll start Bode plots, but we might not actually get to that. So again, last time we were going through an example, digital communication transmitter as motivation for what you're about to learn in this class. And so let's go back to that. So here that is, and again, this is a pretty complex system, and what I'm really trying to get at here, I mean, if you feel overwhelmed about this, you're supposed to. That's what I'm kind of trying to do. I'm trying to let you see, okay, here are all these blocks that you don't know about yet, that you need to learn things to be able to understand how this whole thing works, and that's what we're learning in this class. Okay, so what you're looking at right here is a big system that when you're done with this class, you're going to be able to understand at least how to design a lot of the blocks within these things, or at least get to the point where you might be able to design these in future classes. Okay, but just to review what this was, this is meant to be something like a phone. And so you're going to talk into a microphone of your phone. It's going to take that information and it's going to convert it from the actual analog signal that comes out of your mouth, this EO sound, into an analog voltage. It's going to have to get some amplification to give you that analog voltage, and that amplification is an analog amplifier, something we're going to learn in this class. That's then going to go into what's called the sample and hold, because we want to take that analog information and digitize it for reasons we talked about last time. That being that a lot of processing we do today is digital signal processing, and there's many reasons for that. One, you can store information much better, much more reliably if you store bits instead of storing the analog waveforms, which we used to do several decades ago. Is the sample and hold also an analog component? Yes. I would say it's analog. It's sort of going between analog and digital, because you can claim that it's discrete time, but it's not really discrete time, because if you look what it's doing in this 3A chart, it's sampling the analog signal, which means it could take on any value. So it has a continuous range of values along this axis. and then it's sampling it at a certain time, and it's just holding it at that value. So it's really still putting an output out for all times. So you could sort of say that it is analog. It's continuous amplitude, continuous time, but you can argue that the time now is really not continuous because at these discrete times is the only time this is changing there. But you can consider it analog. The way that it works, it's got a transistor and a capacitor, and you could say that the transistors, it operates more in a digital fashion. It's just kind of on and off. So that's one of those things where you could sort of say it's kind of in between analog and digital there. Now the ramp voltage generator, that's analog. The comparator, that's analog. When we go down here to the binary counter, that's digital. Okay, and so there's no competition between analog and digital. We need both. And in this class, we're going to learn both. We're going to learn more of the analog up front because I guess that's harder to learn. And then at the end, we're going to learn some of the digital. We're not going to be able to cover all the digital you need to know. So beyond this course, you want to take 151 in order to get most of that digital that you really want to understand. Okay, and so after the sample and hold, we get this. Well, I just described what the sample and hold did. We're then going to compare that with a ramp voltage generator. And that comparison is sort of described out here at the far right, where sample and hold goes up here to the analog value that it was at that time. And it holds it there. And this ramp generator just continuously raises this voltage as a function of time until at a certain time it equals this voltage. In that case, now time becomes a measure of what the amplitude of this voltage was. And so as soon as they equal, a bit raises, so the output of the comparator goes up. When that output goes up to a 1, what it does is it feeds to the binary counter, and this is now a command to the binary counter to stop. And so what the binary counter has been doing all this time, all this started at the same time. Once we sampled, this ramp generator started going up, and this counter started counting up. And so we went through that last time. Started at 0, go to 1, to 2, to 3, so on and so forth. And this is happening very fast compared to this encode signal. So in fact, if I had to draw the time waveforms for the encode bit and this clock, it may look something like this. So I'm all the way, whoa, it's very thick. Let me go back here and make that a little thinner. Okay, so I go back here and I can sort of draw an axis on the left side here. And that'll be time. And so my encode signal may be something like this. So boom, it comes up here, and this is encode. And it's on this rising edge where everything turns on. Okay, so it's the rising edge of this signal that we care about here. Yeah, it does drop down here, but it was the rising edge that started everything. It started the sample and hold, it started the ramp voltage generator, it started the binary counter counting. And so the counter now is counting up during this whole time. And so this is the counter waveform. And that's counting up this whole time, 0, 1, 2, 3. And the period that we have goes from here maybe to somewhere out here. That whole thing is the big T. So the counter is going a lot faster than the encode is going to say when to start sampling, etc. So we're sampling right here. I have to remember to point with my mouse. So we're sampling right here. We're sampling again right here in this sample and hold. And all this time this clock is running, counting up to some large number that is a measure of how high this amplitude is. Okay, and so in a way what we've done was we've used a couple of components to create what's called an analog to digital converter. Right, so we've converted this from an analog signal here to a digital number, a quantized number that represents approximately what that analog amplitude was. Okay, and as questions were being asked at the end of the lecture last time, there are many different ways to make this analog to digital converter. This is one way to do it. The other ways to do it you will learn in courses like ee140, ee240B. They involve a stack of resistors or a stack of capacitors, still with a comparator. So the comparator is still in there. There's just different ways to do the comparison. In this case, we're doing it as a basis of time with this ramp voltage generator. You can do it with also a network of resistors or capacitors as well. And there's many different ways to make analog to digital converters. This is just a convenient way for me to talk about that emphasizes some of the basic things that you're going to learn in this class, which is the purpose of this discussion in the first place again. All right, so we have all that. And so, when this stops the binary counter, I have a number. I have 1001 right here. And so what I need to do, since this is meant to be a transmitter, I need to transmit this in electromagnetic waves through an antenna. And so to do that, what I want to do is convert this to a serial stream. Right now it's parallel. I have the 1001 stuck in a register in this binary counter here. If you don't know what a register is, don't worry about that. Think of it as storage there. And so what I'm going to do is send this into what's called a parallel to serial converter. This is another digital block, and this parallel to serial converter will be activated when I give it a read command. Okay, and that read command is going to come somewhere right before my period for sample and hold ends. Right, so maybe my read command occurs right there on this plot that I'm showing to the left here. And so what comes out of the parallel to serial converter is what I'm about to show. So this is the line there. And so let me draw this, say, in, I guess I'll do the time axis in red. So that's time. And so actually what's coming out of this is something that looks like this. So I'm high when it is a 1, and then again when I have a 1. So that's 1, 0, 0, 1 as a function of time. I've basically taken the number 1001 and have now made it 1001 as a waveform. So a stream of bits that are coming out of this now. And so this is the signal that appears right there on that line. Okay, and so the next thing that I have to do in order to transmit this, I can't transmit just this signal because its bandwidth is going to be very high. Square waves, if it's a perfect square wave, have some very high frequencies in them. And I don't want to transmit very high frequencies because if I do that, then that could interfere with other signals that are being transmitted by other phones. And so in this case, what happens is I take this into a low-pass filter. Okay, and so what this does is it band limits the signal before transmission. So let me just say this. This band limits the signal and oftentimes I'm going to use an X to mean trans. You'll see that again and again here. To avoid bleeding into other channels. So I'll say other communication channels. And a communication channel is just sort of the frequency range where you're communicating in. I know I'm talking about things that you may not understand, but if you think of your phone, the way your phone separates your conversation with the conversation of someone else is in the frequency domain. That's something I think you've heard about in the 16s, but I'll say a little more about that today as well, in case you haven't. But now what I've done was I've taken away a lot of frequencies. Okay, someone's writing on my thing here. But from this low-pass filter, I then take this into a multiplier, or a mixer actually. So this is what's called a mixer. And what this does is it translates the frequencies of this, okay, where after low-pass filtering I have a very small frequency. The highest frequency is not that large. But what this mixer does is it sort of multiplies that signal with a sinusoid. So I'll call that cosine omega naught t. And so this mixer is basically multiplication in the time domain. something that we won't learn about in this class, but you can learn about if you take something like 142. This then has to go into another stage of amplification. So we have another analog amplifier. Okay, which then finally gives it enough power. You're amplifying that to give power. So that then finally gets to an antenna. And out of that antenna is your EM signal that's going out into the world and hopefully getting to the person you're trying to communicate with. Okay, and so what happens after mixing with this cosine here, I guess I don't have a lot of space to show that curve, but I'm going to try to show it anyway. Squeeze it in over here. And so after this mixing, let me do that in green so there's no confusion. Let me go from here and go all the way back over here. After I do that mixing, it's actually what you think it is, right? So this is 0 and that's 1, and I'm multiplying that by a sinusoid. Then after that mixing, if this is my time axis, what happens is the 1 turns into a sinusoid. That stops when it becomes a 0 because I'm multiplying the sinusoid by 0. And then when it becomes a 1 again, I get another sinusoid. Okay? And so this is called on-off shift keying. And it's one way to actually modulate information. So when we actually transmit information on an antenna, whenever transmitting the information per se, we always put it on a carrier. That carrier is what's sent off of the antenna with the information on it. And the reason why we do that is because it's easier to transmit at a much higher frequency. And it's easier to multiplex different conversations at much higher frequencies. Okay? And so there's a lot of things that I'm saying there that you just will have to take more courses to understand. This on-off shift keying is also often called OOK, which I've written right there. And so there it is, sort of a complete digital transmitter system going all the way from the microphone to the electronics needed to convert this signal to something that can then be put on an antenna and transmitted out. That's what's received by, if it's a two-way system, your friend. If it's a cell phone system, it's received first by a cell phone tower, and then that tower then retransmits it to your friend who you're talking to. But lo and behold, this is our complete system here. And in the end, like I was saying, this sample and hold here, this I would classify as analog. This comparator, I would classify as analog. Ramp voltage generator, that's analog. Binary counter, digital. Parallel to serial converter, digital. Clock right here. A lot of it is analog. Sometimes it could be digital, but I'll say analog for right now. Low pass filter, analog. Mixer, analog. Analog amplifier, obviously analog. Okay? Lots of analog stuff in this because I'm talking about a communication system. Okay? If I were talking about more of the baseband stuff on the receive side, there'll be tons of digital. Because the receive side has to take the analog information that's received and reconvert it back to a digital format. That then gets processed. And then I guess at the end of that, if it's, say, going to your ear, then it's going to be converted back to analog. So a lot of analog to digital conversions. We need to understand both analog and digital. Okay, so with that sort of introduction, let's get on with the class. Let's start learning the things that we need to learn in order to really understand how to design the innards of all of these circuits that I'm just showing you right here. Okay, let me save this before I forget. And I guess it's taking its sweet time. Should have moved it off the screen first before I saved it. Okay, so now I'll move it off the screen. Okay, so let's get back to the bulk of our lecture. And so let's review analog circuit concepts here. So first of all, I would like to assume that you understand the following concepts from previous courses. And, you know, you may or may not. You should, because I think 16 still cover these things. But if not, let me know. Okay? So transfer functions you should understand. Gain, voltage gain, current gain, power gain, input resistance, output resistance, impedance in general, two-port models for amplifiers. Now that's something you may or may not understand depending on the 16s that you've taken. Bode plots. Old 16s always taught Bode plots. New ones, I'm not sure. I'm getting conflicting information about that. Ideal op-amp circuit design and analysis. I lost my P there. So hopefully you have received some of this in at least 16A. And that's using Kirchhoff's current law with the rules for analyzing op-amps. We will go through all of these things briefly as review, starting right now. So let's start by reviewing impedance. Let me make sure my pen thickness is the right thickness. It is. Okay. Okay, so review of impedance. All right, so if I had a element, just any old element that I'll just describe by a little rectangle, that can be a resistor, a capacitor, an inductor, and if I put a voltage across this element, then I will expect to have a current flowing through that element. And whether that current is in phase with the voltage or not depends on the type of element you have. If it's a resistor, it's going to be in phase. If it's an energy storage element, it's going to be off in phase by a little bit. And so in order to model both the amplitude of the voltage signal and the current signal, I want to use phasors. And so in phasors, when you look at them in books, a lot of times they will boldface them. I don't think anyone here has used a typewriter anymore. But in the old days, when you wanted to say that something was boldified on a typewriter that couldn't boldify, what you would do is put a squiggle under them. So that little squiggle means I'm bold-facing the V and the I, where I'm trying to say that they're phasor variables. So let me just write where the V with a squiggle and the I with a squiggle are phasor variables. Okay, so I assume that you know what a phasor variable is. And so just very briefly, to help you recall, if I wanted to write the voltage signal in the time domain, I may say V of t is going to be equal to some amplitude V prime times the cosine of its frequency, omega, times t, time, plus some phase. Okay? And that would be the time representation of this signal. And my phasor representation, which is almost like a frequency domain representation, but I will not say that outright just yet, it'll be that V squiggle is going to be equal to V prime times e to the j phi, where basically what a phasor is doing is just recognizing that at least for circuits that we care about, which are linear circuits, which means that if a sinusoid at frequency omega comes in, then a sinusoid of frequency omega comes out, perhaps with a different amplitude, perhaps with a different phase, but in most cases it will have the same frequency. It's not until you hit a nonlinear circuit do you actually get differences in frequency. So you may generate new frequencies if you're going through a nonlinear circuit, for example, but those are things you learn deeper down the line in a course like 142. But for right now, this V prime and this phi you can see are the same on both sides here. So you're capturing that information at least in a phasor. And now in a phasor, right, this is a complex number. And so in the end, you know that I can write as an identity, this is the same as V prime, the amplitude, times the cosine of phi. You make that look like phi, plus j times the sine of phi. Okay, so that's a complex variable. And with phasors, you start working with complex numbers, and that's something that you should be familiar with now as well through previous classes. Let me do it this way. So I'll leave that up, and on this side, I'll come down. Okay. And by the same token, this is voltage. I could do the same thing with the current. So I as a function of t, being the current, that's going to be some I prime times the cosine of omega t plus some phi, and I guess I'll call this a phi prime, because depending on what that element is, that could be a different phi. And so I could also put that in phasor form here and write that as I squiggle is equal to I times e to the j phi prime in this. Okay? And so those are your signals, and I think you know signals fairly well. Okay? I'm looking at the chat. I see some questions about still the previous slide, but it looks like they've got answered, so that's good. So now let's look at impedance. Okay, those are our signals. We'll be interested in that, and we're going to be interested, of course, in impedance, because that's one of the properties of a circuit that determines quite a bit whether something is going to do a certain function for you, as we'll see later on in the course. But our impedance, Z I'm going to call it, is going to be equal to the ratio between the voltage and the current across the element that we're dealing with. Okay? And so you know we've got three elements. And so first, we'll look at a resistor. Again, all of these things you should have seen before. So the resistance is just going to be equal to the voltage across that divided by the current across that. And in my phasor notation, which is how I generally would like to think about this through most of this course, that's going to be equal to the V phasor divided by the I phasor. And I think you know, and we'll talk about this more later on, but a resistor is not going to change the phase between the input and the output, in this case between the voltage and the current. So these will be in phase across this resistor. Now a capacitor, another of the three basic elements, it's described by I of t is going to be the value of capacitance C times the derivative of the voltage across it with respect to time. Okay, that's the time domain description of what a capacitor does, the relationship the capacitor makes between voltage and current. The phasor description, as hopefully you'll remember from previous courses, anytime you're taking the derivative of something with respect to time, when you convert it to a phasor, you are taking that dv dt in this case and putting a j omega in front of it. So the phasor form of the same equation here is I is equal to the capacitance value, C, times j omega times that phasor V. Okay, which then tells me, since I'm interested in impedance now, that V over I, the phasor V over I, which I've defined as impedance, for a capacitor, that's going to be 1 over j omega C. Okay? And that's how you've seen it, I think, in the 16s. You may, in the 16s, also have even seen it written as follows, where I'm going to substitute S is equal to j omega. Okay, in which case Z I can write as 1 over SC. So S actually is more general than just more general than j omega. It's actually, it could be a complex number, which means it could be a complex variable. This is something that you will be using not in this class to much extent. In this class, S is going to be j omega. But in a future class that you take in signals and systems, like maybe 120, or especially 128, a controls class, you will start running into the use of the complex variables, where S becomes much more general. But in our case, I like S because it's just easier to write than j omega. Okay, so a lot of times we will start using S. Okay, so those are two of our elements. Let's now get to the third one, which you know is the inductor. And so the expression that relates voltage to current for an inductor is V is equal to L, the inductance, times di dt. And again, I'm taking the derivative of something, so if I want to write that in my phasor domain, V squiggle is going to be equal to that L times j omega times my current. And using the similar arguments as before, that means V squiggle over I squiggle is going to be equal to j omega times L, which I'm also often going to write as S times L. Okay? So some very basics there. I'm sure these are all things that you understand already. And so let's now move on to actually solve circuits based on these types of concepts, signals and impedances. And so let's just do an example circuit, a very simple one. And basically do an example where we're going to determine the transfer function. For this simple circuit. And that simple circuit's going to be this one. So I'll give it some input voltage VI. I'll have a series resistor across here, and then I'll have a shunt capacitor right there, and my output voltage will be right here. Okay, and so when I say shunt capacitor, whenever I say something like shunt, what I mean is that the thing is in parallel with something else. Okay, so shunt sort of is the same thing as parallel, but a lot of times when I say a resistor in shunt, I'm also referring to the situation where that element is going to ground. Okay, so I have that resistor connected to this capacitor. The capacitor is shunt to ground in this case. Okay, just some lingo that you'll hear quite often as we move through this class. And so I can generalize this. So let me go ahead and generalize this to draw a circuit like this, because this leg and this series leg and this shunt leg here are really just elements. And so if I want to generalize this, I could call that, instead of calling that a resistor, call that Z1 to represent the impedance of that resistor. And instead of a capacitor, let's call this Z2 to represent the impedance of that capacitor. And then again, I still have an input voltage and an output voltage. Okay, so you know how to solve this circuit. You know that you can use nodal analysis, and in the 16s, a lot of times you use nodal analysis, I know, in the way that makes it just not very much fun. Okay, and the reason is because I think in the 16s, you learn how to create matrices out of circuits. Okay, now that's an important thing to understand how to do, because people who write programs that solve circuits, like for example SPICE, which is a circuit simulator that you'll be using this semester, that's how it solves circuits. It creates matrices and it does the linear algebra. Okay? But if you're going to solve a circuit, and all the fun of solving a circuit is not in these matrices, right? In this class, you will almost never see a matrix. In fact, you may never see a matrix in this class, because I want you to think of circuits not as matrices and mathematical functions, but as things you can just look at and immediately tell what it's doing. Okay? That's the skill I want you to learn in this class. Okay? And so let's start from the basics and almost do a matrix. I will not make a matrix, but I'll almost do it, because the way you solve these circuits is still the same way. You apply something like KCL, Kirchhoff's current law, or Kirchhoff's voltage law. In this case, I'm going to go ahead and take this as node 1, and I'm going to apply Kirchhoff's current law at node 1. And so if I do that, what's Kirchhoff's current law? It basically says all currents into that node have to sum to 0. Okay? And so instead of summing those currents to 0, let me go to a different color here. Instead of summing currents to 0, what I'm going to say is if I have a current here along that branch, the current, since this is an open circuit, that current has to flow through the other branch. So the current through Z1 has to be equal to the current through Z2. And so I'm going to go ahead and write an expression for this. The expression for the current through Z1, right, which I guess I'll call I1. Let's call that I2 there. Okay, so I know that I1 is just going to be equal to the voltage across Z1, which is going to be VI minus V0 over Z1. Okay, and I2 is just going to be equal to V out, the voltage across the element 2, this is grounded again, divided by Z2. And so in the end, these currents have to be equal. If I1 and I2 have to be equal because of KCL, right? Kirchhoff's current law forces that. Then I can write that VI minus V naught over Z1 has to be equal to V naught over Z2. And if I go ahead and solve this circuit, what I find is that V naught over Vi, and I'm going to say as a function of S, which is the same as the function of j omega, that's got to be equal to Z2 over Z1. That's after I do all that math, over Z1 plus Z2, right? And so this now is the brute force way to solve what this circuit does. But what I want to do now is never do this analysis again. Okay? You do this analysis once. Okay, but if you've done it once, don't do it again. Just remember the answer. So at this point, just remember if I get an L-shaped RC like this, or any Z1, Z2, this is what that is. It's a voltage divider, basically. And so I think from previous courses, you should be able to recognize a voltage divider here. And this is something that I think a lot of you have committed to memory. If you do, that's excellent. That's exactly what you should have done. You should have committed the voltage divider to memory and not do what I just did, the KCL thing there. Now, if I want to relate this to the actual circuit up here, right, the actual circuit then is going to be, I'm going to have to put in the impedances for the resistance and the capacitance in there. And so in this case, I can write that V naught over Vi as a function of S is going to be equal to the impedance of the capacitance, which is 1 over SC, divided by the impedance of the resistance, which is R, divided by, or plus the resistance impedance of the capacitance, 1 over SC. And in the end, I can write this out as 1 over 1 plus S times RC. Okay? And in this case, as you have seen probably in other courses, and as you will see time and time again, the transfer function is a polynomial function of S. Okay? This happens to be a simple one. And if I want to, I can start defining some things here. So, and I usually will, I can call this 1 over 1 plus S times tau. I guess I'll call it tau p, where tau p is an RC time constant that basically tells me how fast this signal is going to change. We'll be dealing with that some more in this course as well. I can also write this as 1 over 1 plus S over omega p, where omega p is a cutoff frequency, 1 over RC. And if I were to plot a Bode plot for this, that would have some significance. Let me just give some of the significance right now. If I wanted to plot my output voltage, V out of t, in response to, say, a square wave input. So say I gave an input that looked like this. If that was my input V of t, then my output is going to look something like this. Okay, where the time constant of that is going to be equal to RC. So there'll be an exponential function going on where the time constant will be equal to RC. If I were looking at this in the frequency domain, and I am talking about things that I have not really discussed completely yet, and I will in just a second, but if I wanted to plot the Bode plot, which some of you know what that is, some of you may not, in this case, And the Bode plot would look something like this, where this would be going down minus 20 dB per decade, and this cutoff frequency here would be that omega p. Okay, so all this information I'm getting out of this simple network that just just from the simple network and the polynomial transfer function associated with it. We'll be dealing with these things again and again and again in this class. So if you don't have a good grip of this right now, you're going to want to get a good grip over the next few weeks here, at least over the next week. Well, you will after this first homework, I suppose. But first, before getting into any of this, let's talk about frequency response here. And so what do I mean by this frequency response? Well, I just showed it as a Bode plot there. That has a lot to do with our understanding of a frequency response. But for frequency response, hold on, I think I skipped, I skipped a slide. Here we are. For frequency response, let's talk about the time and frequency domains, which I think you know about to some extent, but some of you may not know a whole lot about that just yet. But most signals of interest to us can be broken down into sums of sinusoids at various amplitudes and frequencies, that should say frequencies. Okay, and so knowledge of the frequencies and amplitudes of these sinusoids conveys as much about the information content as knowledge of the time-varying amplitude. What that says is that we can think of information either as in the time domain or the frequency domain. Okay, so what is meant by the frequency domain? So very quickly, small definitions here that don't do it justice because you really need pictures to describe it, but a time domain description of information, of a signal, is often conveyed simply by a plot of amplitude versus time. So for example, down here, this is a time domain description of a square wave. Okay, and so these are things you're familiar with. You have seen this many, many times. The frequency domain description, something you will learn a lot more about in 120 and signals and systems courses that some of you have probably seen in 16, is often conveyed by a plot of amplitude and sometimes phase versus frequency. Okay, so let me describe some of these now a little more pictorially. And so in this case, if you're looking at this time domain signal here, this is exactly the same. I will get a square wave if I take multiple sinusoids. And in this case, I would take a sinusoid that is the same frequency as the square wave, that is an amplitude a little larger than this amplitude. I would take another sinusoid that's 3 times the frequency of the square wave at a smaller amplitude. This is going to be about 1/3 the amplitude of that amplitude. And then I would take another frequency component at 5 times the frequency, but an even smaller amplitude. This will be 1/5 time, and so on and so forth here. So here I can put ... here. There's basically an infinite number of sinusoids that I can add together, and if I add all those together, I will get this square wave. Okay, so what this is saying is that the square wave, even though it looks like a square wave to us on this plot, it really is just a bunch of sinusoids. And this is why when we talk about transfer functions in this class, we are always going to think about driving a circuit with a sinusoid and measuring the sinusoid that comes out. Right? We are dealing with a simple signal, the sinusoid, but we're doing that because we understand that any signal, the square wave, the signal coming out of my mouth, which you're hearing right now, it's really just a sum of sinusoids. So to simplify how we talk about amplifiers and transistor circuits, we're going to only shove sinusoids into them, at least in the analog sense. When we get to digital, we'll start putting square waves into them. But in analog, we're always putting a sinusoid in. Okay? And so what I've drawn here, these are all time domain descriptions of our signal. What about frequency domain? Okay, so let me add a frequency domain description. And so how would I describe this in the frequency domain? Well, what I want to do is I want to have on the axis also an amplitude. So this axis is going to be something like signal strength. Okay, same thing as amplitude. And then on the x-axis, instead of time, I want frequency. Okay, so I'm putting frequency along the x-axis and still amplitude along the y-axis. And so in this case, this square wave does not take up all frequencies available. It only takes certain specific frequencies. It takes this frequency, which is f0. Okay, if this is 2f0, and that's 3f0, so on and so forth, then the frequency domain picture of this is going to be some energy at f0. And if the amplitude of this, say, were A, then this energy here would be 4A over pi. Okay? Because that's what the Fourier transform gives me. That's what the Fourier series gives me. If you don't know what a Fourier series is, don't worry about it. But I'm kind of just plotting that Fourier series, but you don't need to understand that. I'm really just plotting this. Go to red here. Right? This sinusoid corresponds to that. Okay? And now I'm going to plot the next sinusoid. Just put its energy in. So this is 3 times the frequency, so it's going to be right here. But its height, the scale here, is only going to be, let me go to red to do that. So that's this. Its height, whoops, is going to be 4A over 3 pi. That's how high that will be. And so on and so forth. This next sinusoid here, which makes up that square wave, this sinusoid goes here, and it is going to be 4A over 5 pi. It's going to have smaller and smaller amplitudes, and so on and so forth. I have more of these all the way out. I have an infinity of these things to make up the square wave. Okay, but it doesn't occupy all the frequencies. It only occupies distinct deltas of frequencies. This is what I mean by frequency domain. And so you could look at this and you could say, this is almost like a Bode plot. And that's exactly what a Bode plot wants to do. Doesn't matter what the square wave is centered around. When we're talking about frequency domain, no. So in that case, what I would have is I would have a DC component here too. I guess if this is DC, I'm going to have some component there that represents this DC in the frequency domain as well. Okay, so it doesn't really matter that much, but you do have to worry about DC and AC in our analyses later on. But what you're going to see us do is we're going to separate them. We're going to do a DC problem, then we're going to do an AC problem, and that's how we're really going to handle nonlinearities, but that's in the future. That's when we hit transistors and how to actually analyze transistor circuits. Okay, so that's frequency and time domain. I don't see too many other questions online, so I'll keep going right here. And so let's now talk about frequency response. And so given what I've just said, to measure a frequency response, this should now be fairly obvious. To measure the frequency response of a given network, I need to excite the network with a variable frequency sinusoid, so like this right here. I need to send that through my network, which I'm calling h of j omega, and at the output, I'm going to get another sinusoid. If it's a linear system, the sinusoid will be at the same frequency, so you see that omega is still there. The amplitude, though, may be different at V0, and the phase may be different. Okay, well, here are the definitions. V0 is the magnitude or the amplitude, and phi, of course, is the phase. Now, the frequency response of the given network, when we measure it, that's where we take the ratio between the output voltage and the input voltage, frequency domain, and we plot those as the amplitude h of j omega, where this is the magnitude of h of j omega, maybe it looks like this, and the phase of h of j omega, maybe it looks like this. So what you're seeing here is that this captures all the information you need right now for a linear system, the amplitude and the phase. The frequency doesn't matter that much because the output frequency, again, is generally equal to the input frequency if it's a linear system. And so it captures the magnitude and the phase, and this actually gives the transfer function for if I put a certain input signal Vi into this, I multiply it by this value to get the magnitude of the output. Okay? These things I think you've seen before as well. Now, what I'm very interested in is plotting these plots. Okay? And I think some of you have done this, some of you have not. Some of you may not have even seen a lot of the stuff that I'm showing right here. And so I might be going a bit fast because, again, this is review to some extent. However, the beauty of this is we have a book. Sedgwick and Smith talks about this, and you can read about this in the book. And he does a very good job. They do a very good job of covering this stuff. All right, so now let's talk about a very specific system here. Let's now start going towards Bode plots here. And let's take a look at Bode plots based on different networks. And so if I have a purely resistive network, like the network that I just had, so let's draw that network again. Whoops, let's make that in black though. Okay, so if I have that same network that I had before, Vi, ground, resistance. Well, let's make a different network. I want it all resistive. Before I had a capacitor in there. So that's R1 and R2. So maybe a simple voltage divider like that. The Bode plot for this is fairly simple. So let me do that same type of Bode plot. So I'm going to plot the magnitude of h of j omega, which is the transfer function of this, right? So h of j omega here is equal to V out of j omega over Vi of j omega. And I'm plotting that magnitude transfer function here as a function of frequency. So I'll make that omega. And then I'm going to do the same thing for phase. So I'll plot the phase h of j omega as a function of omega. And for a resistor, this magnitude is never going to change, right? This is a ratio. This is a voltage divider. I know that h of j omega in this case is just R2 over R1 plus R2 because I've memorized that from last time. Okay? Which means that my Bode plot is just going to be right here. It's going to be a straight line all the way across. It's going to be constant with frequency. Okay? And the value here, again, is this R2 over R1 plus R2. Now the phase change that's going to be given by this resistor, the resistor network, it's not going to change the phase at all. Only an energy storage element can change the phase. Resistor is not an energy storage element. It's a lossy element. And we'll talk about that later on, right, what is meant by a lossy element. But in the end, in this case, the phase doesn't change. So this is zero phase, and it just stays zero all the way across this Bode plot. So this is a Bode plot for a resistor, for this resistive network here. Okay, this is probably the simplest network I could possibly come up with here in terms of drawing a Bode plot. But don't worry, things get much more interesting once we start adding our energy storage elements. And so if I were to add energy storage elements, I would start getting a transfer function like the one we got for the resistor capacitor. So if I go back a couple here to my resistor capacitor network, remember this now had this transfer function. It has an S in it. And so in general, these transfer functions will be polynomials. And so if I wanted to write this out in an equation format, I can do the following. So on the left side now, let me get a black pen. H of S, so I'm going to use S because j omega is just going to take too much space with this big equation I'm about to write. That's going to be V naught of S divided by Vi of S, which is going to be equal to some resistive term. So I'll just outright call this my resistive term. It has no frequency dependence, times a whole bunch of things that depend on frequency, and that means that depend on S. So I can write this as S minus Z1 times S minus Z2, dot, 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 all the way to S minus Zm. I've drawn that line too long. That divided by S minus P1, S minus P2, dot, 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 to S minus Pn. Okay, where I can also write this in shorthand form as H naught times the product. I'll say J equals 1 to M of S minus Z sub J, and the product of I equals 1 to N of S minus P sub I. That is a very general transfer function where, you know, I've got all these different things defined. Z sub J is equal to a complex number. So sigma Zj plus J omega Zj in the most general sense. Okay, I can have a complex pole like that, or a complex zero is what this is. But right now, a lot of this is just symbols and math. And that's fine if it's just symbols and math here for you. So sigma sub Zj is going to be the real part of Z sub J, obviously. Omega sub Zj is going to be the imaginary part of Zj. And Zj is a zero. Okay, so some of you mentioned you don't know what poles and zeros are. This kind of tells you what poles and zeros are. They're really just mathematical constructs in the way we're looking at it here that describe these polynomial transfer functions. Now, they'll have much more significance when you get to a class like a controls class. And even in 140, where we start talking about compensation and instability, which is a controls topic. But that's sort of where this is. So I'm going to finish this up next time. We're out of time this time. So I will see you on Wednesday where we will continue with all of this stuff. And now...
Professor?
Yes.
Quick question.
Go ahead.
So for the homework, I was taking a look at it, and there seems to be like a lot of problems that haven't been covered in lecture. So like, what do you recommend for like the timeline for like doing homeworks? Like, should we wait till like something is covered in lecture and then do the corresponding problems, or
so this
like, should we start earlier?
Yeah, this will probably be the only homework assignment that is not covered in lecture yet. Most of our homework assignments I'll cover it in lecture and then you'll have it before you do the homework. Sometimes I'll get to the lecture like on the Monday, the week that it's due. Hopefully not all the time Wednesday, the week that it's due, but sometimes that might happen. But I'll at least get lectures in for everything. This is the only one that's not the case for, because this homework is supposed to be things you already know. Now, I understand that might not be the case for some of you, so if that's the case, I would say read the book, and then by the time I get to Wednesday lecture, I'll have covered everything for the homework. But yeah, so don't worry too much about that. Try reading the book if you don't understand some of the questions in the homework, or, you know, stay online, and I'm going to office hours right now, in fact. Unfortunately, my office hours are in a different Zoom link, so what's going to happen is we're going to leave this meeting, and then those who want to get to office hours show up to that other Zoom link. I'll be there. Okay? All right. So, yeah, let me quit the lecture here, and if anyone has more questions, ask them in office hours in just a couple minutes here. Okay? All right. But I'll see everyone either in office hours or very soon.